So let's go ahead and get started. The first thing we're going to do is take a look at what we have created so far. I've gone ahead and I've created a project where I want to calculate shipping. And we do this by providing some various information such as the state at which we're shipping to, the weight of the product, and the size of the product. And what we do at this point is we grab some modifiers that will allow us to calculate a shipping rate and return it. We're doing this because in order to prove multi-threading, you need to actually perform some actions. Our program is very straightforward. It's a simple console application that will generate some product for us. And we can provide it an X to leave, a single to perform as non-task, and tell it to be threaded, and it'll run it as threaded. So let's go ahead and take a look at what this would look like in a non-threaded environment. So let's go ahead and go into my run as non-parallel. And I'm going to go ahead and create a new instance of a stopwatch because I want to be able to determine how long this thing takes. And we'll do stopwatch.start here. Do stopwatch.stop down here. Then finally what we're going to do is we're just going to iterate over our products and calculate the shipping cost one by one. And that's it. Pretty straightforward for loop. Once we get inside our calculate method, we're doing a couple different things, grabbing the modifier, the weight modifier, the size modifier, calculating all those things together, determining a shipping rate off that, and return it back. So before we run this, let's go and add a console.writeLine to this so we can see exactly how many milliseconds it took to process our items. So let's go and run this, see how long it takes. I'm going to tell it to run in single threaded mode. And it took 502 milliseconds to process 1 million items. That's not too bad, but what kind of improvement can we see if we actually just parallelize this? Now, to parallelize this using the task parallel library, it's pretty straightforward. I'm going to be able to use almost the exact same syntax with this minor tweak. So let's actually go ahead and copy, just so we don't waste some time here. Now in the non-parallel we actually use a for loop. Well, in the parallel I need to use the for each loop that is attached to the parallel namespace, which is part of the system.threading.task namespace. And I'm going to say for each, and the first argument is your list. And then here we're actually going to specify a lambda syntax. And inside of here is when we're actually going to perform our calculation. And your X is the instance of a single instance of the list that you're working with. So we can use x.state, x.weight, and product size. And that's it. Now, fundamentally, my for loop has not changed in the least. I've just specified it as a Parallel.For So let's run this again. So let's just go and run this again as a single threaded. It took 489. How about if I run it threaded now? Alright, so shaved about 140 milliseconds off. One thing to understand when you start utilizing multi-threaded and paralleling is that you need to make sure you have pure methods. You got to make sure that the state inside of your functions don't change objects outside of its control, because if that's the case, you're going to start running into some race conditions and get some weird threading scenarios. Now, in our example here, we just use the default parameter list for Parallel.For But what if I have, say, an 8-core machine, and I don't want to use all 8 cores for processing because I don't want to tie up all the resources? How could I get around that? Well, fortunately the designers have thought of this for you, so they actually allowed you to provide the max degree of parallelism for this run. And to use this, you just need to do new parallel options and provide it the max degree of parallelism. I'm going to go ahead and say 1 for now. And basically what 1 will do is if I run this, it will run it as a single core machine. So let's go ahead and run this again. And we're going to run this in single thread mode just to get our baseline, 507. And you'll see that there is a little bit of overhead to run it in the parallel mode when I'm only utilizing a single core. Let's run this again, see if I can get any better results. And a little bit better results. If I tweak this max degrees to be 2 and run it again, I should see my original performance come back. You'll see that my multi-thread, multi-core does actually utilize more cores and actually runs things a little bit faster. So that's how we can utilize the Parallel.Foreach. How can we go about utilizing the Parallel.For? Well, to utilize Parallel.For, all you need to do is, let's comment this out. Just use Parallel.For, and you need to tell it a from and to. So we'll say from 0 to products.count, and provide it the action or the function. We're going to go ahead and tell it an action here. In our scenario here, X is not the instance of each element, it is actually the index. So what we can do here is we can say, var and that's how I can utilize my for syntax instead of the for each. And in fact, you can still provide your new parallel options for this as well if you'd like to change the max degrees of parallelism. And that is how you can utilize both the Parallel.For and Parallel.Foreach syntax, which is part of the new system.threading.task namespace. And it really simplifies parallel programming on multi-core machines. So I'd encourage you to dive into this, see how your products can utilize it with .4.0, and see what kind of improvements you can make or you can see on your applications. And I hope you learned something. Till next time.